Camera action. We good? All right, welcome to another exciting episode of AP Chemistry here at Spain Park High School. Today is Friday, December the 1st. Yeah. If you are enjoying these long, boring AP videos, please hit that like button because you are going to learn something anyway. Okay, so today we're going to hopefully just have a lot of time to work on your own, but I want to go through some of these gas law problems together and look at some from previous, AP tests. Yesterday we talked about Raoult's law. Okay, so if we look at last year's test, okay, we go to here this is 2023, and we look at this particulate view right here. Okay? Now, it says a particulate level diagram of an equilibrium mixture of aluminum chloride and Al2Cl6 at 400 degrees in a 25-liter closed container is given. Now, it says on F, it says calculate the value of Kp. Now, we don't know how to do Kp yet. That's going to be, yeah, I gave them to you yesterday.
It's not in the packet.
Oh, this isn't in the packet, but I want you to have the packet out because we're going to be going through those. But this is just a question we can just do in our head right here, not in the packet. Okay, so I'm going to go through some old AP tests just kind of as examples. Then we're going to look at some of the packet. Then I'm going to let you go on your own. Okay, but this I meant to show you this when we were talking about Raoult's law. Okay, because to calculate Kp, you need to know the partial pressure of the AlCl3 and the partial pressure of the Al2Cl6. Okay? Now, if I know the total pressure is 22.1 atmospheres, this is making up the whole thing. The pressure of this is 22.1 atmospheres. How can I, using Raoult's law, I don't know why I look at you. Okay, using Raoult's law, can I determine what the AlCl3 and the Al2Cl6 partial pressures are going to be?
Mole fraction.
What about it?
Mole fraction times the total pressure.
Okay, so what does that mean? So how many molecules do I have total? 10. How many of them are AlCl3? 7. 1, 2, 3, 4, 5, 6, 7. So 7 of the 10 molecules are AlCl3. So what does that mean about the pressure? 70% of the pressure is due to AlCl3. Well, what's the total pressure? 22.1. So 70% of 22.1 is due to AlCl3, right? Obviously, then the other 30% is due to this. So once you just multiply those out, Kp is just a ratio of the two. We'll learn how to do that. But once you get that part, the rest is easy. Okay? So that's just an application of Raoult's law. Okay? Now, which one is going to next? Now we just go down to this next one, 3A, and this is just a review. This has nothing to do with gas laws, but I want you just to see, I want you to do 3A. I want you to write the net ionic equation for that equation. What's the net ionic equation for that? It's not in the packet. You can just do it on the back of the packet. You can just do it somewhere. I just want to review writing net ionic equations. None of these that I'm going over on the screen are going to be in the packet. But this is last year's test. You can look it up. square. Now, first thing, what is the definition of an ion? Charged particles. So therefore, when you dissociate these into ions, what must you always include? The charges. Okay? Now, what's the only state that actually does dissociate? Aqueous. And those aqueous, what are the only aqueous ones that dissociate? Strong acid, strong base, soluble ionic. Okay? And you would know it's soluble ionic because it's going to have AQ right there. Okay? Now, how do we know our strong acids? They're up there for right now, but how are we going to know them in May?
Memorized.
We're going to have memorized. Our strong bases, though, remember, make the block lowercase b, lithium, sodium, potassium, rubidium, cesium, strontium, and barium hydroxide are your strong bases. The lithium, sodium, potassium, rubidium, cesium, strontium, and barium strong hydroxides are your strong bases. They're the only ones that are going to actually dissociate. Now the reality is the strong bases are ionic compounds anyway. So if it's an ionic aqueous, it's going to be dissociated. If it's not aqueous, it's not going to be dissociated. So the bases really aren't as important to memorize because they're going to ionize anyway. Now, we do want to know them. So is this going to stay together or ionize? Dissociate. Stay together. So it's CaCO3 solid. But what about this? Why does it now in this one it's covalent. Acids, we don't say dissociate. Acids ionize because technically in the gaseous, in the pure form, they're sharing electrons. But when they go into water, the water actually is the home wrecker. It breaks the bond and causes the ions to form. So we say they ionize in water. Ionic compounds dissociate in water. Covalent compounds, acids, ionize in water. Okay? Slightly different terminology, but same effect. So what are we going to get? 2H pluses and 2 Cl minuses. They are not going to be in a subscript 2. The 2H pluses are not going to bond together. Right? Now, calcium chloride is an aqueous ionic, so we're going to get Ca with what charge?
2 plus.
2 plus. And
Cl minus.
how many?
2 Cl minus.
2 Cl minuses. Because it's going to be a Ca 2 plus bonded to a Cl minus, bonded to a Cl minus. These two are not going to bond together, so it's not going to have a subscript 2. Each one of these are going to break and get surrounded by water molecules, so we're going to get 2 Cl minuses. We need to be familiar, your halide ions are monatomic ions. Okay, so the hard part is to know when does the subscript become a coefficient and when do you keep it. That's why we have to know in a polyatomic ion, the subscript stays. Okay, so we're going to get 2 Cl minuses. That's where a lot of people miss the boat right there. Plus what? Does CO2?
Nope, and H2 do not.
They both stay together, right?
So the only thing you cross out is 2 Cl minus?
Yes. So, and what do we call those?
Spectator.
The spectator. So, you know, if you're doing this and you do the total and you're on the test, if you're doing it in pencil, you can just erase this. Okay? Or you just rewrite it. I don't think, if you did that, I don't think they'd give you credit. They might. Okay? I would prefer you just erase it or rewrite it the correct way. Okay? So just erase it and get that. okay?
I think that's the first one we've done where only one
Yeah.
gets crossed out.
And again, it's just the state. Just remember, only aqueous and only your electrolytes, which is your aqueous or soluble ionic, strong acids, strong bases. But again, your strong bases are going to be aqueous ionic, and your strong acids, you just have to know the 6. All right, so that's just review. You will have those on the exam. Okay. So now, if we go back up to here, well, that's 18, there's 19, okay? Let's look at, now, again, review what we just did, just to show you that it's on the test. This is last year's test still. The boiling point of bromine is 332, BrCl is 278. Okay? Explain this difference in terms of intermolecular forces between molecules of each substance. Okay? Well, this is what type of substance? What's the intermolecular force between bromine molecules?
London.
LDS.
Yes.
Bromine is totally nonpolar. The difference in electronegativities is 0. Okay? So the only IMF are LDFs. Okay? Whereas this one, is it going to be totally nonpolar?
No.
No. So what type of intermolecular forces are going to be between the molecules here?
LDFs and dipole.
And LDFs. But because this boiling point is higher than that boiling point, what does that mean about this?
LDFs got more.
The LDFs are greater because
A more polarizable electron cloud.
it's a more polarizable electron cloud because it's a bigger electron cloud. So I would say the reverse way, because the Br2 is a bigger electron cloud than the BrCl, it is more polarizable, allowing it to have stronger LDFs than the combined LDFs and dipole-dipole of BrCl. And stress again between molecules. But this could have been on the last test you just took. Right? So we need to know that. That's why we're doing AP Academy, making sure everything that we talked about we're going to be comfortable with. All right? So we just, again, get it, keep working through it to where you're comfortable. All right, but this is the one I want us to see. Okay? D. This is how they throw it in there. A 0.1 mole sample of BrCl is placed in a previously evacuated rigid 2-liter container at 298. Eventually, the system reaches equilibrium according to the equation above. But calculate the pressure before equilibrium was established. Again, in your packet, just on the back. Let's see if you can do that.
What was the temperature again? You got to cut off. Is it? It was 278. It's to the right. 290.
50. All right, we should be done by now. Okay, look, calculate the pressure. I'm given a volume, I'm given a temperature, and I'm given moles. What equation am I going to use? Ideal gas law. PV is equal to nRT. Therefore, P is equal to nRT over V, 0.1 times, okay? It does not say what unit to calculate it into. Therefore, you can use 0.0821 or 62.36. Okay, either one. Both of those are given on the equation sheet. My go-to is the 0.0821. Now, I said 0.08206, I think is what I gave you yesterday. So 0.08206 times 298 divided by the volume, which is 2 liters. And everything is 3 sig figs, so we get 3 sig figs. What's my pressure to 3 sig figs in atmospheres?
1.22.
1.22 atmospheres. Okay? So that's how they throw in gas laws. Notice this is not a gas law problem. This is an equilibrium. This is what makes AP Chemistry hard. Because this is not a gas law problem. It's not an intermolecular force problem. It's not just an equilibrium problem. It's a thermochemistry problem, equilibrium, gas law, it's a chemistry problem. You don't just have one concept in the problem.
It's 12.2.
12.2?
Yeah. 0.0821 times 298 divided by 2. Oh, it's 0.1. Yeah. Okay, never mind.
Okay. When everybody's got the other one, I'm gonna say probably left a decimal off somewhere.
Yeah.
Okay, so again, that's the challenge, is that we can't get our brains into a box. Is that we have to look at all the different things and say, okay, well, KP takes me here, delta H takes me there, okay? Again, that's the challenge of this, okay? But this is where they throw gas laws in, just like this. This could probably be one of the extent of the gas law type problems, okay? So now we can go down to 3. Well, we don't need to do another net ionic equation, but that would be a good practice for you studying for the exam. Okay, notice these are all aqueous. Now just real fast, let's just do this. What are my spectator ions going to be in this one? Whatever's the aqueous one over here. Now because it's aqueous, this is like the normal one, what Luke's talking about. Aqueous, 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 solid. I know that these are my spectator ions, okay, NAs. So it's really, my net's going to be CO3 2 minus plus Ca 2 plus going to Ca CO3 solid. That's my net ionic equation. I just get rid of my spectators. Okay, so that one's pretty straightforward. But in this diagram below, drawn the species needed to accurately represent, okay? So we just did this. Let me first off say, let me make it a little bit smaller so we see it all. A student is given 50 milliliters of sodium carbonate of unknown concentration. To determine the concentration, they use excess calcium nitrate, causing a precipitate to form. There's your balanced equation. There's your net ionic, okay? So now we have this. You have your solid calcium carbonate. That's your precipitate that formed, okay? You have your Na, NO3, okay, that were spectator ions. What else is missing?
Excess reactant.
The excess.
Say that again.
Excess.
The excess. Excess 1 molar calcium nitrate. Okay? So I've got to have some calcium in there. I have to have some of the excess reactant in there. Now, How many calciums, do you just randomly put calciums in here? What do we have to make sure is balanced? The equation, but NaNO3, NaNO3, NO3, NO3.
Two CAs.
I need two CAs?
Oh, because it was CaNO3 too, wasn't it? Is that what it was?
What's the charge on calcium?
Plus two.
Plus 2.
So it's
One.
Ion,
One.
huh?
You only have one.
Again, let's don't say words out. Let's think about this. Okay? We had CaCO3 forming as a solid. Okay, we had NaNO3 as my spectator ions floating around. Okay, but we have excess of this. Pardon me. We have excess of the sodium carbonate. Okay? We have excess. Done? Now, y'all, in a solution, everything's got to be balanced. Everything's got to be neutral. It's got to be, so.
Where's the chemistry?
NaNO3, NaNO3. How many calciums do I need?
One.
Just one. Calcium is a +2 charge.
You put the excess as the one.
Calcium nitrate.
There we go.
Well, again, I'm trying to go through.
That's still wrong. Still not it.
No,
And it's not, it's calcium nitrate.
Yeah.
Thank you.
It's still not it. There we go.
Okay, the whole point, that's irrelevant. It was excess up here. We only need one calcium to balance it out. Okay, so two things you need to take from this, despite all the going around. Number one, you have to always pay attention to excess. Number two, the solution is always neutral. I was actually at the reading for this year. I didn't grade this question, but this question was highly missed because people just threw in calciums all over the place. They didn't worry about balancing the charge. They remembered excess, but they just put in a bunch of calciums, and no other nitrates. Now, if you put in more calciums and more nitrates, that's fine. It just has to stay balanced. But the easiest thing, all they wanted you to do is put one calcium. Okay? All right. That's 2018 right here.
Oh no.
Okay? This is just again a review of, I'm just kind of showing you on last year's test why what we just did was so important. Okay? The Lewis dot structure. What are the steps of drawing a Lewis dot structure? Count the valence electrons. 1 plus 5 makes 6, plus 12 makes 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay? Actually, start on the peripheral, make that your central atom. The hydrogen's on this is my central atom. Okay? Is this nitrogen satisfied?
No.
No. Got to form a double bond. Now, I'm not going to form a double bond with this one because oxygen can only form 2 bonds. I'm going to share with this one and make that double bond. Okay?
So if you left it like that and you didn't move the far right electrons to where it would actually be configured, would they count off, or if you just left it like that, would it be fine?
That's exactly how you're supposed to do it in the box. What do you mean?
No, that's never mind. It's fine.
He means the
Like,
way
some of
the
the-
way
Say
the
like
electron
there's
pairs
electrons,
are
like, would
organized.
you have to shift them, or would they just
It doesn't
count
matter.
Well, you just need to have 2 lone pair on this one and 2 on that one.
Okay, so
Yeah, the way you organize them.
But, I mean, the way I had it like this originally, before I did it, if I did that, okay? Now, again, as long as you went to here and not to here. As long as you did that and did there, you're gonna end, well, no, you're not. I gotta count again. We're 2, 4, 6, 8, 10, 12, 14, 16, 18, there's 18 there. Okay, so if I did it like this, here, okay? If that's what you're saying, that's how I originally had it. Now it's gonna be, you're gonna want to go, if you do it like that, you're gonna wanna put the double bond there. But why is that not gonna happen? Oxygen's gonna form 2 bonds, not 3. Okay? So I'm gonna share, this needs the 8, I need to share there. So it's really gonna be those on that one.
What would the shape be?
Well, the shape is gonna be around each central atom. So this is gonna be AX what? AX2E. AX2E bent. What's the type of hybridization on the nitrogen?
SP2.
sp2. 3 electron pair domains. sp2. Okay? We need to be able to do Lewis dot structures. Okay? Now, if I'm doing that, if I'm looking at HNO2, I count 18, I'm just gonna go oxygen, oxygen. I know the hydrogen's gonna go there. Then I go 2, 4, 6, 8, 10, 12, 14, 16, 18. That's how I would normally just draw it. So then, I know I need to have the double bond, so I go there. So you might want to maybe draw it on the outside how you typically would do it, then make a match in the box. Okay? But then that's, again, AX2E. 3 electron pair domains is always going to be sp2 hybridization. All right, enough review. But all these things that we're just looking at, this is all last year's test, or last few years test. Okay. Yes.
Why can't oxygen have 3 bonds?
Because it has 6 valence electrons, it only needs 2 more, it cannot have an expanded octet. It's too small to have an expanded octet.
So like you can't erase 2 and then have like the 3rd bond.
No. I say all that, but in carbon monoxide, the only way you can form, and this is the only time, and I have no idea how it actually bonds, but in carbon monoxide, you have 4 and 6, you have 10 electrons. So you have carbon, oxygen, 2, 4, 6, 8, 10. Well, the only way to get the octet rule is to go here and go here. But you don't have any other choices. There you got choices. Generally speaking, oxygen is only going to form 2 bonds. This is the only time in the history of my teaching career that I've seen oxygen with 3 bonds. And the last I read, about 30 years ago, was that the bonding was not understood. Okay? But just kind of keep that in mind on carbon monoxide.
How about the acid?
All right. Oh, now, let's see here. Here we go. Here's another question from 2019, I believe. All right, I want you, this is in your packet. This is in your packet. Okay? What did I say? Okay, listen. Time-wise, this is considered a short free-response question. You would need to estimate 12 to 15 minutes max on this question. Let's try to get it done in 8. I can't pause it with my phone. iPhones don't let you pause the video. They'll just fast forward. You're watching at 2 times speed anyway, so they'll just fast forward to 2 times. But they should stop and be working this problem as they're watching the video.
It's coming out regular.
I'm already sleeping through.
You know, you have all that space below that you could write it in instead of trying to cram it in between the 2 little lines. Okay, just saying.
Wait, is this how it's like on the?
No, on the exam they give you lines, but in 2019, they gave you a separate booklet with lines with the questions in it. But they get it like this, and then you answer in the lines. However, when we were reading, there were students like y'all that would cram them in between, even though they had 3 pages of lines after the question, they would cram it in between.
Yeah, you like front and back like 4 times, and then you all just kind of crammed it in the first section.
Okay, one more minute. All right. So first, we have this, we raise the temperature of 299 to 425. Describe the effect of raising the temperature. In a simple phrase, what's the answer? Heat them up, speed them up. But in more technical terms, by increasing the temperature, what are you increasing?
The average kinetic energy.
The average kinetic energy, which means the molecules are moving faster. By increasing the temperature, you're increasing the average kinetic energy, which causes which means the molecules are moving faster. Basically, you need to say the molecules are moving faster. You got to say more than heat them up, speed them up, though. Okay, that's the concept. Now, I think I have to stand corrected here on this one because I've said I hardly ever see Boyle-Charles Gay-Lussac's law used. Okay, calculate the pressure at 425. What you do, all you have is temperature and pressure. Okay, you don't have any moles or grams or anything in order to be able to use PV equals nRT. So, but the relationship, we know that the relationship between pressure and temperature are directly proportional. So it's P1 over T1 is equal to P2 over T2. So then we can just plug in, the initial pressure is 0.7 atmospheres. The initial temperature is 299 K is equal to the new pressure P2 divided by 425 K. Now I hope that your algebra is good enough where you know you just bring the 425 up here. You don't go through cross multiply and then redivide everything out. Okay, the 425 just comes up here. So it's this times that divided by that. And what's the pressure equal? 0.99.
9918.
And it's 2.99, and that's going to be in atmospheres. Okay, did yours work out? Okay. Because you had volume in there. And you didn't need. What did you use for N?
Well, I substituted
Oh, you said PV equals nRT.
another,
Or,
N over V equals.
okay. Yeah, I mean, these just, but that's really, they're all related to one another. The N's just cancel out because it's the same number of moles. Okay, so in terms of kinetic molecular theory, that's what we talked about yesterday. Briefly explain why the pressure in the CO2 changes. Well, what causes pressure? Collisions with the container wall. Why does increasing the temperature increase the pressure? Because the molecules are moving faster, so hitting more frequently and hitting with more energy. There are more energetic collisions, both of which cause an increase of pressure. Okay? Now, I don't know if you have to have both of those. I need to just go check real fast whether you have to have both of those, but for sure at least one of them. The molecules are moving faster, so they hit the container walls more often, but they also hit more energetically at the higher temperature. Both cause an increase in pressure. And then lastly, why don't we get the predicted?
Because this is actual attractive forces.
Okay, it's attractive forces. Okay. Ideal gas has no attractive forces, but CO2 molecules will have IMFs or intermolecular forces. These attractive forces cause the pressure to be less. You don't have to get much. This is only 1 point each. You don't have to get much more. It's the fact that ideal gases, the molecules exert zero attractive forces, whereas CO2 is actually going to have some IMFs, weak as they are, but it's going to cause it to deviate some from ideal behavior.
Can they calculate the speed of ideal gases?
Well, they can calculate the speed of a real gas, you can't calculate the speed of an imaginary gas that takes up no space. But it still have a mass, it still has the mass, so yes.
Yeah, because they still have a mass.
But I mean, what mass are you gonna use if it's an imaginary gas?
Use I.
You just know, what you do is you just use a real gas and you just assume there's none of the other things in there.
Yeah.
And you just use that real gas as if it were an ideal gas. Alright, so those are just examples that we can go through. Now, the rest of the packet you should be able to do on your own. Okay? Now, let's just talk about a time frame. We've already done one. We went through, we did this one, right, with the total pressures? Okay? I think we did the second one with a total pressure as well on the next page. Didn't we start in on number one or the example one?
Private safety gas laws problem?
Yeah,
No,
We haven't done it.
okay.
all we did was the multiple choice.
Okay.
And then that thing.
I know, but I'm just trying to do a timing. What's y'all's test schedule look like? You can turn it off.
We have a test.
Next week.